Hi, I'm Eliane Wiese, presenting It Must Include Rules, Middle School Students' Computational Thinking with Computer Models in Science. This is an example of a computer model that middle school students might use to learn about science. This one shows how plants survive short periods of darkness. A cumulative graph shows the running total of glucose made and used, and the amount in storage. What is this model trying to teach us? Figuring that out involves thinking through how this model works. Without knowing exactly how the model is programmed, we can make some good guesses. There are probably variables that keep track of the amount of glucose made, used, and stored. While the plant is alive, the glucose used increases. We can tell because the line for glucose used just goes up. The cumulative glucose made goes up when the light is on, but stays flat when the light is off. Also, in the light, total glucose made rises faster than total glucose used. This means that in the light, glucose is made faster than it's used. So our variable for total glucose made increases when the light is on and increases more than the total glucose used. Glucose stored is what's left over after taking the total that's been made and subtracting what has been used. Getting to this pseudocode relied on knowledge of how computers work. They execute logical steps, they store values, they update values. Reasoning from this pseudocode shows a lot of the ideas that this simulation is intended to teach. Plants use glucose continuously, but they need light to make it. They can survive short periods of darkness by storing glucose, but when that stored glucose runs out, the plant will die. A middle school student might summarize how this model works by saying, plants need light to grow. That thinking misses most of the ideas that the model is intended to teach. Getting at the science requires students to identify at a high level the rules the model is following. Can they? To find out, our assessment items presented models that the students had already learned from in their science classes. Students decided, for each proposed statement, if it was a rule that the computer model was following. This kind of item showed that students were missing key concepts from the models. Only 57% of students correctly said that the simulation was following the rule total glucose used always increases. This follows a common student misconception about the science, that plants only use glucose in the light. If students don't realize what behaviors the model is demonstrating, they won't be able to learn those concepts from the model. 40% of students incorrectly thought that the model was following the rule plants use carbon dioxide in photosynthesis. Real plants do, but carbon dioxide is not part of this model, which, like all models, is a simplification. Many students thought that the model could follow two rules that contradicted each other. Still, questions about the rules help elicit student science ideas. A typical science question about this climate simulation would ask about the relationship between two variables in the model, like the greenhouse gases and the temperature. The answer, the more greenhouse gases, the higher the temperature, explains the outcome. An answer with mechanisms would explain the greenhouse gases trap the infrared radiation inside the atmosphere and redirect them back towards the Earth. This makes the temperature rise. With this typical question, only 11% of answers included mechanisms. But asking students to think about rules almost doubled the answers that included mechanisms. A rule-based question asked what would happen to the temperature if all of the sunlight was reflected. Students could not test this rule, they had to imagine it. Compared to the typical question, many more students included mechanisms in their answers, like saying, it would cool down because it would not convert light energy into heat. Thinking in terms of rules may help students communicate their science ideas, and may even clarify those ideas for themselves. Takeaways. Even with pre-built models, we can make the computation more explicit so that students get needed practice thinking about it. We should continue examining the kinds of computational thinking that students need when they use computer models of science phenomena. Our results show that students struggle to identify model rules, to tell which variables are included in a model, and to distinguish science concepts from operationalized rules that a computer program could follow. We also show that prompting students to think about model rules can elicit important science reasoning, indicating that computational thinking and science learning can support each other. Please check out the paper for more details. Thanks.